See. Good. So this is the lesson 5, right? So today we get to the theory, to the actual theory. I will start building it. I'm not going to derive the theory from classical GR or anything like that. I'm going to write the theory, and then talk about the connection to the classical theory. So LQG, and I will build the theory in 2 steps: the kinematics and the dynamics. So I'll start from the kinematics. I'll say exactly what I mean. Today is the kinematics. So in general, the structure of a quantum theory in general is a triple: a Hilbert space, an algebra of observable, and something giving the transition amplitudes. You might think the space of the wave function of a particle, the position and momentum operators, and the Hamiltonian, and which says how things change in time, or instead of the Hamiltonian, the path integral, or instead of the path integral, just the transition amplitude, the unitary operator that evolves e to the I t h. In QED, this is Fock space. This is the A dagger operators, the creation-destruction operators, and again you have either the Hamiltonian or you have the actual the Poincaré group on the Fock space, which includes evolution, or the Feynman rules, and so on and so forth. Right. So this is a general structure of quantum theory. This is what I call kinematics. This is what I call dynamics. It's just names. Nothing deep about that. Now, in the kinematics, so we'll focus on that part for today. In the kinematics, the important part is the algebra. The Hilbert space is actually a sort of auxiliary structure. The core of the thing is here, is not here. When Heisenberg wrote his first paper on quantum mechanics introducing the theory, there was no Hilbert space, it was only the algebra. He called them matrices, right? He just had this idea of transforming variable into matrices, x and position and momentum became matrices. When him and Jordan and Born developed the full structure of quantum mechanics, so that was before Schrödinger, there was no Hilbert space. It was just the algebra of operator. So the structure at the time was, this thing was PQ, or QP is IH bar, and then there was, this was Q dot. So A dot for any observable is IH bar, I don't remember where it is, a commutator with a Hamiltonian. So you see there's no Hilbert space here, there's just operators. So the Hilbert space, it's really an auxiliary structure to better work about the algebra, but since Schrödinger and Dirac and von Neumann, it's much easier to write, instead of an abstract algebra, a concrete algebra of operators, a Hilbert space. So I'll follow that, even if conceptually it would be more clear to start from that. But I follow what is usually done in quantum mechanics to define the Hilbert space first, and then it's easy to write operators on the Hilbert space. But the core is here, and what is physically the algebra? Where is the thing that describes the variables? The physical system is described by variables, right? A particle is described by its position, its velocity, its momentum, its energy, if it has structure, angular momentum, and so on. These are all variables. Classical mechanics, you describe a system with variables. In quantum mechanics, you describe a system with variables. Same. In quantum mechanics, these are often called observables. It's a it's a slightly misleading name because observables is sort of idealistic thing. There's the eye of the scientist or God or whoever who observes. Okay, in distant galaxies, there's nobody observing, but they're variables, and variables describe system and describe how system interact with other system. So it would be good to stop talking about measurement in quantum theory because there's no measurement when there are no scientists, but there are always interactions. And the way systems affect one another is via interactions. And these interactions, how systems affect one another, are described by variables. So if I throw a piece of chalk against the blackboard, where it hits is a variable of the piece of chalk, and the effect of the interaction is that. Okay, so this the algebra of the variables, and here what we are actually describing is a gravitational field, which is a piece of general relativistic space-time, which is a piece of space-time in the Newtonian sense. So it's a region of space-time. Okay, so what we are describing is a region of space-time, or a four-dimensional piece of space-time, which interact with the rest through some variables. It's metric, whatever, and the interaction is on the boundary. So this variable sits on the boundary. Okay, variables sit on the boundary of a four-dimensional compact region. They're going to be essentially the metric and the time derivative of the metric on the boundary here. And then the dynamics will tell us how we go, say, from here to here. How they propagate, how they evolve, what's the relation between the different points here. This will come slowly. And as I said, the easiest way to define the operator here the variable here is operator on a Hilbert space. Why? Because that's quantum mechanics. That's Heisenberg, fantastic discovery. The variable for a system form a non-commuting algebra. When you multiply them, it's not the same. XP is not the same as PX. So it's a non-commutative algebra, and from the non-commutativity, all the quantum mechanics stuff follows. The easiest way to describe a non-commutative algebra is to think of them as an algebra of operators. Heisenberg would think of an algebra of matrices. We are going to follow the standard way and think as an operator on Hilbert space. Again, thinks X and P operator for a free particle on wave functions on space, or creation operators on Fock space for QED. Good. So that's the starting point. So as I said, I will first define H and then define the operators on H. So H. So this is the Hilbert space of loop quantum gravity, and it's going to be more like the Hilbert space of QED or QCD than of particle, because it's a field theory. It's an infinite number of degrees of freedom. And if you think what happened in QCD on the lattice or in QED, the clean way of defining Hilbert spaces for an infinite number of degrees of freedom is to define them for a finite number of degrees of freedom, then take some sort of limit. In the clean way of defining Fock space is to define one particle Hilbert space, then a two particles Hilbert space, then three particles Hilbert space, or more precisely, the space of states up to 3 particles, up to 4 particles, up to 5 particles. So you have the state space of 0, 1, 2, 3, or 4 to 5 particles, and then this is called n, and then you take n to infinity, and that's your Fock space. If you think, when you have done calculations in QED, you never take this limit for real. The limit is just written on the mathematical books. and you can prove fancy theorems. But if you're at CERN and you want to compute scattering of particles, use Feynman graphs. But Feynman graphs, you work up to some order, and up to some order, there are always a finite number of particles, and never an infinite number of particles. Right? So you actually always work on Hilbert spaces for a finite number of degrees of freedom, arbitrarily large. So it's limited in this sense. And that's what we're going to do. If you think of QCD, the other way, there are two quantum field theories we control where, right? QED and QCD. QED mostly perturbative, Feynman graphs. QCD a little bit perturbatively in the deep inelastic scattering, for instance, but a lot on the lattice. And the lattice we do the same thing. You define a finite lattice, and that's QCD on the lattice, and then you compute things, and then you take the lattice sufficiently fine with the number of lattice space n, and when it's large enough, you think that this is good enough. And you have theorems that tells you that if you increase n, your results don't change much. So here we're going to do the same. We're going to define this as a limit in some sense, which I'll say later, of something which I call gamma going to infinity of H gamma, where H gamma is the Hilbert space of loop quantum gravity of a truncation of the number of degrees of freedom. I'll say what gamma is in a moment, and then what it means to go to. And concretely, we'll work with H gamma most of the time, and don't bother much about the limit. So what is gamma? And here we start coming to the triviality. It's a graph. And graphs sit naturally inside one another. Given a graph, I know what is a subgraph. So these Hilbert spaces will sit naturally one inside another. So you can always take the larger one, and the more large you go, the more degrees of freedom you capture. So what is a graph? A graph is a couple of two things: a set n. How do you do n? And a set L, where n is just a finite dimensional set, is a finite dimensional set with n elements, which we call little n, and we call nodes. So in other words, this is 1, 2, 3, 4, 5, 6 things. Okay. L is a collection of ordered couples of elements of n. So an element little l of this thing L is the other way around. Is just n1, n2 ordered. So you can think it's a little arrow here. It's one way of representing it. And L is a collection of these. So say this, and 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 this. This is a graph. What matters of the graph is not how you write it on the blackboard or how it's embedded in space-time. It's just a combinatorial who is connected to whom in the link, how the links connect the nodes. So sometimes, to make it clear, this is called combinatorial graph, to distinguish it from one of these things embedded in R3 or in a given manifold, which is an embedded graph. This is an abstract combinatorial graph. It's just combinatorics. So given a link, since it is oriented, there is the node it starts from and the node where it arrives, which are called the source of the link and the target of the link. These are two nodes, two elements here. Given a node, there are a certain number of links coming out of them, oriented, either coming in or coming out. And the number of links is called the valence of the node. So number of links is called the valence of the node. It's a little bit terminology of graphs. Now, how do you think about these graphs? Well, there's a particular subclass of graphs which are of interest for us. Think about the surface, a curved surface, and imagine to triangulate it. What does it mean to triangulate it? It means to draw little triangles over it. Okay. Now, once you have the triangles, these triangles are attached to one another in a combinatorial way. You know who is next to whom, and you can think of putting a dot somewhere in each point, in each triangle, one per each triangle, and connect them. And so on and so forth. And you get a graph. The graph that describe how the triangles are connected to one another. Sorry? Oh, thank you. Means a big graph. It's going to be when you take this n going larger and larger in some suitable sense. Thank you. So a set of triangles connected in this way is called a triangulation. And triangulations, a given triangulation is usually indicated by a delta. And the graph dual triangulation that I've written down, this blue graph. So the graph obtained by identifying any triangle with a node and any two adjacent triangles with a link is called a dual triangulation. It's called delta star, and is a graph up to the orientation of the link. So if you have a way to fix the orientation of the links, it gives a graph. So by itself is a non-oriented graph. I'm not going to talk about the orientation for the moment. It's a peculiar graph because all nodes are trivalent, right? Because they're inside the so nodes here are trivalent. So the valence of the node is 3. Now we can do the same in 4 dimension. And in 4 dimension, so you have some piece of space, and you can break it in tetrahedra. This is a tetrahedron. Okay, and you can think that inside of each tetrahedron you have a point. You pick up a point, and when 2 tetrahedra are nearby, you connect them by a link. So you get a graph, exactly like before. So you have a triangulation, and you have a dual triangulation, and this defines a graph, which is 4-valent. And we are gonna.
Did you say 4 dimensions or 3 dimensions?
Sorry?
Is this 4D or 3D?
3D. 3D. This is 2D. This is 4D. Okay. We are going to be interested in graphs which are dual of triangulations. A subclass of class which is dual to 3-dimensional triangulations. And quite often, most of the time, loop quantum gravity is defined on this set of graphs, but not necessarily. In fact, that's already one option you can have when you start defining loop quantum gravity. You can say, well, I want to work with all possible graphs, or I want to work only with graphs which are dual to triangulations. Does this give different theories? Nobody knows so far. Okay, so somebody works for arbitrary graph. Concretely, when you work, you try to work with graphs dual to triangulations up to the point in which it's too hard and easier to use more general graphs. You'll see how this goes. Here, let's work with graphs which are dual to four-dimensional to triangulations. So I'm going to consider graphs which are four-valent and such that there is a four-dimensional triangulation that for which they are the dual. But the important part is the graph is not the triangulation. Notice that I've not talked about any metric flatness, curvature. This is just about who is next to who. Pieces of things and who is next to who. So this sort of captures the adjacency of the notion of space I was referring to on the second lesson. So, just to have this clear, since it's gonna come over and over again, a node, if you think in terms of a triangulation, is dual to a tetrahedron, and a link is dual to two nearby tetrahedra which are separated by a triangle. So tetrahedron, triangle, node, link. So digest this like if it was, yes?
I have a question. So if I have triangles that hinge around the points, they will be a little circle as a graph, as a dual graph. Whereas if I have a band of triangles that don't hinge on points, well, there will still be a circle as a graph. So I'm wondering whether your graphs are annotated somehow in a way as to be able to distinguish whether they come from a band or from a disk.
You're saying the same graph can come from different triangulations, that's what you're saying?
Yeah, from very different geometrical objects.
No, they're not. The structure here is only this one. Keep this only in mind as a reference, which we'll use when we interpret that in space-time terms. But the theory is built only on this structure here. Four-valent graphs, oriented four-valent graphs. Good. So they have no other information than this one. Well, let's go to it. So I have one of these graphs, four-valent, etc. Actually, let me just not have open ends. I have a graph, and I'm going to now tell you what the Hilbert space associated this graph is. And I'm going to first define a larger Hilbert space, and then the actual Hilbert space will be a proper subset of this, which is defined as follows. Imagine that to each oriented link you associate an element of SU2. So there is a family, there are L, so say there are L links. Capital L is the number of links. So you have one SU2 element for each link, so the L element, and you consider wave functions which are functions of this L element of SU2. Well, the Hilbert space is just L2 of SU2 to the L, namely the set of these wave functions here. That's a home in which we're going to work. That's like Fock space. No, not really Fock space. That's like the space of particles up to n particles, roughly, or L particles. And that's like the space of wave functions of a particle, and so on. In fact, it's very similar to the Hilbert space of lattice QCD. In fact, it is a Hilbert space of lattice QCD. If you take this graph to be cubic, that's how you do lattice QCD, which is also a truncation of the full theory. Now, just hint how to think about these things. Well, these are just suggestions will become clear later, but I don't want to go ahead abstractly without giving you an idea of what it means. Think that this surface to start with was curved, hills, okay? And think that I have approximated it with little flat triangles, okay? Then each triangle has its own geometry. The length of this, the length of this, the length of this. If I know the geometry of each triangle, I know the curvature of the surface, right? Because they don't, for instance, this triangle here, this triangle here, this triangle here, the angles here don't pile up to 2 pi, so there's some curvature here. So that's how I approximate the curvature of a surface. So we'll have in this Hilbert space operators that correspond to the geometry of the tetrahedra, which will define the curved three-dimensional space. Now, another way of thinking about that is that if I have on this triangle here a orthonormal frame, and I move it parallel to itself here, and I move it here, I move it back here, because there's curvature here, it can be rotated, right? So anyway I orient my reference frame here, here, and here, moving from here to here, I can have a rotation matrix that does it, another rotation matrix, another rotation matrix. When I do a tour, the product of the 3 rotation matrix is actually the curvature. We measure the curvature here. If this is flat, I can orient my reference system whatever I want, but when I come back to myself. If it is curvature, I come back curvature, rotated. This is a way of defining curvature, in fact. You know that on the Earth, if you parallel transport something, you come back, and it's not, you get back rotated, because that's what curvature is. So you can think to associate a rotation to each line here, and the lack of when you go around, if the rotation is 0, there is no curvature here. There's a rotation is here. Now you can do the same in 3 dimensions. And in 3 dimensions, so now you're inside this tetrahedron. You have a 3-dimensional frame. You go to this tetrahedron, to this tetrahedron, to this tetrahedron, to this tetrahedron. Each tetrahedron is flat, but if you come back rotating, there's curvature along this bone here, right? So all these rotations associated to the jump from one tetrahedron to the other, so in the dual triangulation to the links. So you have a rotation associated to each link. When you make a tour, if the product of them is not identity, there is curvature here. So in this way of thinking, you describe geometry by associating a rotation to each link of the dual graph. So an element of SO3 to each link of the dual graph. That's exactly what we're doing. We have an element of SU2 to associate it to each link of the dual graph. So if this is a tetrahedron, this is a tetrahedron, this is a tetrahedron, this is a tetrahedron, you go around and there's curvature because you have going around. So these are the classical variables. The quantum state associates an amplitude to a set of classical variables. Yes?
So can I think of this SU2 as a parallel transport?
Yes.
Just in space?
Yes, in space. That's right. Exactly. Exactly so. And the Hilbert space is just the amplitude for having one set of parallel transports or for having one geometry. And of course, the general state will be a linear superposition of different geometries. So it's a state over geometry. That's what we're going to describe. So we're going to describe quantum geometries. This is the space of quantum geometries. This will come out slowly. For the moment, I've given you a precise definition of the Hilbert space and a hint of what is behind it. Now, there's still this tilde, and I said that the actual Hilbert space is going to be a subspace of that. Why? Well, let's go back to our...
what is the orientation of the link? I mean, what is the physical meaning of the orientation of the link?
None.
No. Okay.
None. The final result should be the same if I take one link and orient it the opposite way. It's just because when you actually want to assign an SU2 element to that, you have to say the SU2 element is assigned to the link oriented this way, and to the opposite orientation you have to assign the opposite, the inverse of the... So just to be able to work and to start naming things, you put an orientation, but the actual choice of orientation is irrelevant to anything you compute. Good. So I was saying that the actual Hilbert space is going to be smaller than that. Why? Well, my discussion that told you why. I said I choose a reference frame here, and when I go around and come back, that's give me the curvature. But if I had chosen a different reference frame, it would not matter, right? I can choose a reference frame the way I want. So there's some redundancy here in the description, some gauge, and the redundancy is the arbitrary is a rotation without it inside each tetrahedron. So in each node here, if I rotate my frame, so if I rotate all the group elements that come out from it in the same manner, nothing should change. So in other words, we want a gauge. We want to say that there is a gauge, exactly like in lattice QCD, which takes HL, the SU2 group element associated to a link, and gauge transform it into HL multiplied by some group element lambda on the source of the links, and lambda minus 1, a different group element associated to the target of the link. So I have gauge transformation. What is a gauge transformation? A gauge transformation is a group element lambda for each node. For each node, I choose a group element, an SU2 group element. And I want this to be a gauge transformation, meaning what? I want my state to be invariant under that. So I want not to consider all those wave functions, but only a subset of those wave functions. The wave functions that have the property that h of L is equal to lambda source of L, h of L, lambda minus 1 target of L for every choice of lambda n in SU2, or let me change notation, set of this in SU2 to the n. So the gauge transformation is one SU2 per node. Okay? So the set of the wave functions here that satisfy that equation is what I call H gamma, which is a subset of H tilde gamma, is a proper subset. It's a SU2 is compact. So there's no infinity here. Okay, it's I'm dividing by a compact group, and the usual notation of these things is SU2 to the L, so L group elements divided by SU2 to the N, which of course this is a space. So is the Cartesian product of L copies of U2 divided by the Cartesian product of N copies of U2. But of course you have to know how to divide, and this is how you factor out. So it's good to put a little gamma here. Otherwise this notation here seems to say that this is independent of gamma. This depends on gamma. So this tilde space here doesn't really know about the graph. But this until the space knows a lot about the graph, so it knows deeply about the structure of the graph. Yes.
Psi lives in H tilde or H?
Sorry.
Psi lives in H tilde or H?
The psi we're going to work about live in H. Okay. H is a subspace of H tilde, so they also live in H tilde. Okay.
So this condition is what allows them to be in H, because initially you
right.
said it was in H tilde, but with this condition it's in.
With this condition is an H. H is a set of elements of H tilde that satisfy these conditions, the definition of H. It will be good from now on to work always with H, but it's much more complicated. It's much easier to go back to H tilde every time you. So in other words, it's much easier to work with non-gauge invariant things and then to pick up the gauge invariant part, as usual in gauge theories. Good. Basically, that's it for the Hilbert space. And as I said, the Hilbert space serves for building the algebra. So let's start building the algebra. And we're going to build the algebra on gamma, sitting here. Well, it will have two parts. X and P, creation, annihilation, field at fixed time and its momentum, the standard in quantum mechanics, so the non-commuting part. There's an abelian subalgebra, which is super easy. These are functions of group elements. So I can multiply by any function of group element, and that's an operator, the diagonal operator, the analog of X operator acting on psi of X. Just multiply psi of X by X. Okay. So any function of L, capital L group elements is an operator here, which means that everything that I can measure related to the parallel transport, as you were saying, is going to be an operator in this Hilbert space, very simply. Now you do find written HL operator psi of HL is equal HL psi of HL in articles and in books. It's a little bit confusing because this is a group element. This is not a number. So what the hell does it mean? What it does mean is that the matrix element AB of this one are operators, okay? Or any function of the group element. For instance, the trace of that is an operator who's that act on this by multiplying it, just the trace. of it. So when you find this notation, this means matrix element by matrix element. That's the easy part. The interesting part is the other half, the momentum, and we want some derivative operator. IH bar d over dx, the analog of p psi of x being minus IH bar d over dx of psi of x. So we want some derivatives, and we do have a derivative, right? I just defined for you a derivative on the group, which is a left invariant vector field. So we'll have a left invariant vector field L as an operator, and we'll have one for each copy of the group. So this is all going to be labeled by links. These are certainly well defined in H tilde. Are they well defined on H? No. Why? Because H are gauge invariant things, sort of invariant under rotation if you want. This is a vector, it's never going to be invariant under rotation. If it's a vector in this Hilbert space here. If here I rotate with a gauge, this is going to transform in the representation of spin 1 as an index I. It's going to be transformed with that index. So this is going to be an operator here. Out of this, we're going to construct gauge invariant operators here. So this is going to be the main object we're going to work with, and I'm going to tell you how out of this I construct gauge invariant operator here. I'm going to tell you what is the geometrical interpretation of this object, and what then the quantum theory says about this geometrical interpretations, but this will be the next hour because it's the end of the 45 minutes. Do you have questions before? This is the ABC of loop quantum gravity. Okay? We're just putting all the basic blocks, and what is going to happen in the next lecture is to build, work, see what this operator do, and what this interpreter mean, and we'll immediately get some physics out of that. Okay? Let's stop here.